Hello! This lesson will be looking at properties of exponential functions. So let's investigate. Graph each equation by completing the table of values. Label each equation. So let's start with y equals 2 to the power of x. So to begin with the table of values, we'll set our x values to -3, -2, -1, 0, 1, 2, 3. Now to determine our y values, we're going to substitute our x values in for our exponent. So 2 to the exponent -3. Recall working with negative exponents. We can flip our base. And we now have a positive exponent. 1 to the exponent 3 is just 1. So then we're left with 2 to the exponent 3. To expand is 1/8. If we were to calculate (1 divided by 8) equals 0.125. Okay, we'll do the same with -2. 2 to the exponent -2. We want to make our exponent positive. 1/2 to the power of 2. 1/4 to equal 0.25. 2 to the exponent -1 is just 1/2, which in decimal form is 0.5. 2 to the exponent 0, again, exponent laws, anything to the power of 0 is 1. Nice and easy. So now 2 to the exponent 1. Now our exponents are positive, so it's just 2. 2 to the exponent 2 is 4. And 2 to the exponent 3 is 8. So now that we have created our table of values, we can plug in our points. So at -3, we're plotting 0.125. So here's -3. 125 is really close to 0. -2 and 0.25. Again, still really close to 0. At -1, we see that it's 0.5. A little easier to graph. At 0, we have a point at 1. At 1, we have a point at 2. At 2, we're at 4. And at 3, we're at 8. So we connect the dots, okay? Property with exponential functions is that it never crosses the y-axis. So we'll get really close to 0, but it'll never be 0. And as we notice, we exponentially grow. So we grow really fast as our numbers get bigger. So this is the equation for y equals 2 to the power of x. So let's look at our second example, y equals 1/2 to the power of x. So again, we'll substitute these values for x. And to calculate y, we sub our x values in for x. So 1/2 to the power of -3. Again, negative exponent. To make positive, we flip our base. There's 2/1 to the power of 3, which is just like saying 2 to the power of 3. which is 8. 1/2 to the power of -2. We flip our base to get a positive exponent. 2 to the power of 2 is 4. 1/2 -2. This is not 2, this is 1. So we now have a positive 1. This 2 to the power of 1 is 2. 1/2 to the power of 0. Remember, anything to the power of 0 is 1. 1/2 to the power of 1 is 0.5. 1/2 to the power of 2 is like saying 1/2 to the 2, which is 1/4, which is 0.5. And 1/2 to the power of 3 is like saying 1/2 to the power of 3. One over 8, which we know is 0.125. So let's graph this one. So at -3, we have a value of 8. And -2, we're at 4. And -1, we're at 2. 0, we're at 1. 0.5. We get smaller and smaller and closer to 0. Okay, so connect our dots. So as we can see here, we start off on a high, but we reduce the bigger our numbers get. So this is an exponential decay. So we said this is a growth, and this is a decay. We can also notice what determines our growth and decay is our base value. So here, having a number greater than 1, which was 2, offered us a growth. And here our base is a 1/2, which is between 0 and 1, and we're decaying. So these are what exponential functions look like. But let's recall the features of a linear and quadratic function. So linear table of values has constant first difference, graphically they are lines, so we have positive and negative, and our equation y equals mx plus b. Our quadratic functions, second differences are constant. Our graph, we have positive parabolas where we're opening up and down. Our negative quadratic functions. Our equations, we have 3, but I'll just write here one in vertex form. Okay. So for an exponential function, the equation is y equals bx. Oh, let's see. So we can see that there. We'll flip the page. We'll summarize some of the properties. So if, please include the b, is greater than 1, then the graph shows increasing growth. where the larger b produces faster growth. If b is between 0 and 1, the graph shows a decay where the small b produces faster decay. Exponential growth and decay graphs have a horizontal line that the graph gets increasingly close to but does not intersect, and this line is called the horizontal asymptote. So the table has the first difference. So the table has first differences that have a multiplying pattern. So let's look at this example. Classify as either linear, quadratic, or exponential. So first, to test linear, we're looking at the first difference test.